A chip that should not exist just went into production in China. No extreme ultraviolet lithography machine touched it. No banned equipment from the Netherlands. No restricted tools from the United States. None of the multi-billion-dollar hardware that Washington spent years trying to keep out of Chinese hands. And yet, according to the engineers who built it, this chip performs like something years ahead of what its manufacturing process should allow. Somewhere in Shanghai, a woman known inside her own industry as the Chip Queen stood on a stage and said her company had been quietly building toward this moment for 6 years. Nobody outside her lab knew. Nobody in Washington saw it coming. And by the time the rest of the world understood what she was describing, the first version of it was already shipping inside phones. This is the story of what China just showed the world, why it matters far beyond one company or one country, and why some of the smartest people in the semiconductor industry are still arguing about what it actually means. Right now, in fabrication plants scattered across southern China, engineers are running the same production lines that were supposed to have stalled out years ago. Right now in Washington, policymakers who built an entire export control strategy around one piece of machinery are quietly reassessing whether that machinery was ever the whole story. And right now, inside Huawei's own semiconductor division, the team that spent 6 years working in near silence is finally being asked the question everyone wants answered. How did you actually pull this off? To understand why this moment carries weight, you have to understand who made the announcement and where. The presentation happened at the IEE International Symposium on Circuits and Systems, known as ISCAS, one of the oldest and most respected academic venues in electrical engineering, held in 2026 in Shanghai. This is not a marketing keynote dressed up as science. IEE conferences are peer-facing, technical, and unforgiving of hype that cannot survive scrutiny from other engineers in the room. The presenter was He Tingbo, chairwoman of Huawei's Scientist Committee and president of the company's semiconductor division, HiSilicon. She is not new to this fight. She was already a senior figure inside Huawei's chip operations when the company got hit with the sanctions that were supposed to end its ambitions. What she unveiled at ISCAS was something Huawei calls the Tau scaling law, paired with a production architecture called logic folding. And by the end of her talk, semiconductor analysts everywhere were asking the same question. Did Huawei just find a way around the wall the United States spent years building? Here is the plainest way to understand what changed. For 50 years, the entire computer chip industry followed one guiding idea, known as Moore's law: pack more transistors onto a chip by making them smaller. Smaller transistors, closer together, meant more computing power in the same physical space. It is the reason your phone today does more than a supercomputer did decades ago. But shrinking transistors requires extraordinarily precise manufacturing tools, and the most advanced of those tools, extreme ultraviolet lithography machines, are built by a small handful of companies and tightly restricted from export to China. Think of it like a city that can only grow by building its buildings ever thinner and packing them closer together on the same street. Eventually, you run out of room to shrink, and if someone else controls the specialized cranes needed to build at that scale, you are stuck. Huawei's answer was to stop trying to shrink buildings altogether and instead build upward. Picture a city that can no longer expand outward, finally deciding to construct skyscrapers, stacking function directly on top of function, so a signal traveling through the system has a shorter physical distance to cover. That is the essence of logic folding. Instead of laying circuits flat across a two-dimensional silicon wafer, the architecture folds and stacks logic layers vertically, bonding them together. The goal is not smaller transistors. The goal is a shorter path for electrical signals to travel, which is where the name Tau scaling law comes from. Tau, in engineering notation, represents a time constant, specifically the delay it takes for a signal to propagate through a circuit. Huawei's argument is that once transistors get too small to shrink further without hitting, physical limits measured in mere atoms, the smarter lever to pull is not size, it is time. That physical limit is not exaggeration. Modern transistor features are now measured in distances so small that a handful of individual atoms lined up in a row would span the same width. Engineers across the entire chip industry, not just in China, have been warning for years that traditional geometric shrinking is approaching a wall where quantum effects, heat dissipation, and manufacturing tolerances stop cooperating no matter how much money gets thrown at the problem. Huawei's bet is that the industry was going to be forced to confront that wall eventually anyway. Sanctions, or no sanctions, and that arriving early gave the company a head start on whatever comes after Moore's law, rather than a consolation prize for being locked out of it. If you want a sense of just how significant a shift that is, consider this. The current global leaders in chip manufacturing, companies like TSMC in Taiwan, are pushing toward what is called a 1.4 nanometer manufacturing process, a scale so small it is difficult to compare to anything human-sized. A single strand of human hair is roughly 80,000 nanometers wide. Now picture that same hair, but imagine trying to carve a functioning electronic pathway 50,000 times narrower than its width, using light itself as the cutting tool. That is the physical territory the industry has been racing toward for 2 decades. Huawei is telling the world it does not need to win that race in the traditional sense. It says its tau scaling approach can deliver performance equivalent to that 1.4 nanometer class of chip, without ever manufacturing an actual 1.4 nanometer transistor. Now here's the part that connects everything back to why this took people by surprise. This was not a rushed reaction to sanctions. He Tingbo told the ISCAS audience that Huawei had been designing and mass-producing chips based on tau scaling principles for 6 years before this announcement, dating back to roughly the same period the company's access to advanced lithography tools was first cut off. Over that stretch, according to Huawei, the company designed and mass-produced 381 separate chips built around this philosophy, feeding products across smartphones, telecommunications equipment, and AI computing hardware, long before the world had a name for what it was looking at. That is not a company scrambling after being blocked. That is a company that appears to have started building an entirely different road the moment the old one was closed. 381 chips. That is not a prototype. That is not a lab demo built for a single conference slide. That is a running production history spanning 6 years, quietly built into products that were already sitting in people's pockets and on cellular towers long before anyone connected the dots. He Tingbo herself framed it that way in her keynote, telling the audience in Shanghai that 6 years earlier, when geometric miniaturization first hit a plateau for her team, the company made a deliberate choice to rethink what Moore's law even meant for a business locked out of the newest lithography tools rather than wait for access to return. Trade publication EE Times. Asia, which covers the semiconductor industry closely across Asia, reported that Huawei validated its approach using the same 381 chip production history, describing the shift as a move from optimizing for geometric size to optimizing for time compression at every level of the design stack. That detail matters because it is a second independent outlet describing the same core claim Huawei made on stage, rather than Huawei's announcement standing entirely alone. Let's pause and restack what we know so far. In 2023, Huawei stunned the world by releasing the Mate 60 smartphone series with a 5G-capable chip built on 7 nanometer technology, a feat many analysts assumed was impossible under sanctions. That was the first shock. 3 years later, at ISCAS 2026, Huawei revealed that the Mate 60 breakthrough was not a one-time trick. It was the visible tip of a 6-year, 381-chip campaign built on a completely different scaling philosophy, one designed specifically to make lithography restrictions less relevant over time. Now let's get into how that philosophy actually becomes hardware people can hold in their hands. Logic folding operates on what Huawei describes as 3 coordinated levels. At the device level, engineers optimize the resistance and parasitic capacitance inside individual transistors and their connecting wires, minimizing the physical source of signal delay at the most basic layer. At the circuit level, logic folding breaks apart the traditional flat layout of a chip, folding critical circuit pathways into a compact vertical structure that dramatically shortens the wiring a signal has to travel, which reduces both resistive and capacitive load during signal propagation. At the system level, Huawei layers on something called a unified bus, an interconnect protocol designed to give large clusters of chips a shared, unified way of addressing memory, cutting communication delays not just inside a single chip, but across entire server systems built from many chips working together. Independent semiconductor analysts at the research firm Futurum Group described Huawei's approach as a genuine reframing of the packaging competition, one that stacks at chip layers vertically rather than spreading them flat, delivering a jump in computing density roughly comparable to what the industry would normally expect from several years of traditional shrinking, achieved without new lithography tools at all. Here's where it gets tangible. Huawei is not describing this purely as a research concept sitting in a lab. According to the company, the Kirin processor line, scheduled to ship in flagship smartphones in the autumn of 2026, will be the first commercial products built on the logic folding architecture, meaning ordinary consumers buying a new Huawei phone this year would be holding the first mass market proof of this approach. Trade publication Tom's Hardware, which covers semiconductor announcements closely, reported that Huawei is targeting a 55% increase in transistor density using this method, positioning it as a direct attempt to close the technology gap with global chip leaders like TSMC and the American chip designer NVIDIA, whose most advanced AI processors currently sit out of reach for Chinese buyers under existing export restrictions. Reporting from EE Times Asia added that the Kirin 2026 chip specifically adopts what Huawei calls a free logic design concept, extending its processing core architecture in ways engineers say could eventually push clock speeds toward 4 GHz, a meaningful jump for a mobile processor built without access to the newest lithography nodes. And this is not a story that stopped at the initial announcement. Roughly 2 months after the May 2026 unveiling, Huawei released an expanded technical paper referred to as version 2 of its Tau scaling framework, according to reporting from the semiconductor research firm TrendForce. That follow-up document outlined a roadmap extending logic folding well beyond phone chips, projecting the architecture would eventually reach Huawei's Ascend line of AI accelerator chips, the hardware category most directly competing with the AI processors, made by American companies like NVIDIA, with a target window around 2030. The same report projected that if the roadmap holds, transistor density under this approach could climb dramatically higher between 2026 and 2035, driven by advances in low-temperature bonding techniques that allow chip layers to be stacked without damaging the layers beneath them. There is also a supply chain dimension worth naming here, because a chip architecture does not exist in a vacuum. Huawei's chips are physically manufactured in partnership with Semiconductor Manufacturing International Corporation, China's largest contract chip maker, commonly known as SMIC, which produced the 7-nanometer chip inside that original Mate 60 phone. Following Huawei's announcement, shares in SMIC rose more than 7% in a single trading day, a reaction that signaled investors saw the Tau scaling approach as directly tied to SMIC's own manufacturing future. SMIC has separately been investing in what the industry calls post-Moore's Law pathways, including setting up a dedicated advanced packaging research institute in Shanghai earlier in the year, the kind of facility built specifically to support exactly the sort of vertical chip stacking that logic folding depends on. There's also a question worth sitting with here, because it changes how you should read everything that follows. Huawei's leap is not happening in isolation. It is arriving inside a broader wave of Chinese technological announcements that landed in close succession through 2026. If you have made it this far, you already understand why engineers on both sides of the Pacific are paying close attention to this story. And if that is the kind of breakdown you want more of, subscribing helps this channel keep digging into the announcements that actually matter instead of the ones that just make headlines. In the same window as Huawei's presentation, Chinese state-backed manufacturers began mass production of the country's first domestically built immersion, deep ultraviolet lithography machines, a category of chip-making equipment one tier below the most restricted extreme ultraviolet tools, but still central to producing modern chips. Industry reporting indicated that initial output would remain modest, with roughly 5 machines expected to ship during 2026 before scaling toward 20 machines in 2027, giving Chinese chipmakers their strongest domestic alternative yet to Western lithography systems. Chinese research teams also brought 3 separate quantum computers online in the same year, each built on a completely different physical approach. One used photonic qubits, one used superconducting circuits, and one, developed by a team at the Chinese Academy of Sciences Cold Atom Technology Group in Wuhan, trapped roughly 200 individual rubidium atoms using tightly focused laser arrays, arranging them into what researchers described as a dual-core architecture capable of running parallel quantum calculations, while a second core handled real-time error correction. None of those developments are the same technology as Tau scaling, but together they paint a picture analysts inside China have started describing openly. Less a single breakthrough than the convergence of years of parallel investment across robotics, chips, and computing all becoming visible at once. Xiang Ligang, Director General of a Beijing-based industry alliance focused on information technology, told reporters that what looked like a sudden wave of announcements was really the surfacing of a comprehensive capability that had been building for years beneath the surface, not the product of any single project succeeding overnight. What makes this so different from past claims of catching up is the framing itself. Huawei is not saying it has matched Western chipmaking. It is explicitly arguing that the entire industry's decades-old measuring stick, the relentless shrinking described by Moore's Law, is running out of runway for everyone, not just for companies under sanctions. If that argument holds up under scrutiny, Huawei would not just be finding a workaround. It would be proposing an entirely new axis for the whole industry to compete on, one where owning the most advanced lithography tools stops being the decisive advantage it has been for 50 years. To be clear, this is where the story needs to slow down. There is a meaningful difference between what Huawei has proven and what Huawei is projecting. What has genuinely happened and has been independently reported by outlets, including the South China Morning Post and trade press, covering the ISCAS presentation directly, is that Huawei presented a real technical framework, backed by 6 years of design history and 381 previously produced chips, at a serious peer-facing engineering conference. That part is not speculative. What remains unproven, at least publicly, is the headline claim that this approach will deliver performance equivalent to a 1.4 nanometer manufacturing process by 2031. That figure comes from Huawei itself, has not been independently verified by a neutral third-party lab, and describes a projected outcome roughly 5 years out, not a chip sitting on a bench today. Analysts at Futurum Group and other independent semiconductor research firms have been careful to note that TSMC and Intel still hold a commanding lead in raw process node development, with TSMC currently manufacturing at a 2 nanometer scale and planning mass production at 1.4 nanometers by 2028, while both companies continue advancing their own hybrid bonding and advanced packaging roadmaps in parallel. Nobody serious is claiming Huawei has surpassed the world's leading chipmakers today. The honest claim is narrower and still significant. Huawei may have found a way to keep improving chip performance meaningfully without needing the machines the United States has been blocking, which changes the long-term math of the sanction strategy, even if it does not erase the current gap. It's also worth separating population-level industry trends from a single company's specific promises. Huawei's own success does not automatically mean every Chinese chipmaker can replicate this approach, and yield rates, real-world power efficiency, and manufacturing cost at scale for logic folding chips remain largely undisclosed, outside Huawei's own figures. Even the widely cited 55% transistor density increase and the 1.4 nanometer equivalence claim are figures Huawei itself generated. And as of this reporting, no independent lab outside the company has published a teardown or third-party benchmark confirming those numbers hold up under real world conditions at scale across millions of units. A single flagship phone chip performing well in controlled demonstrations is not the same thing as a mature, high-yield manufacturing process proven across an entire product line for years, which is exactly the kind of track record TSMC and Intel already have. So where does that leave things? The sanctions that were designed around a single assumption that controlling access to extreme ultraviolet lithography machines would control the pace of Chinese chip advancement were built for a world where shrinking transistors was still the only path forward. Huawei's Tau scaling announcement is a direct challenge to that assumption, whether or not its 2031 target proves accurate. And here's the part that circles back to where we started. That surprise Mate 60 chip in 2023 was not the end of the story. It was the opening scene of a much longer one that Huawei had been quietly writing for 6 years, before anyone outside the company knew the plot. The chip queen, who once had to explain how her division survived being cut off from the world's most advanced chip tools, stood on a stage in Shanghai and effectively said the wall itself might no longer matter the way everyone assumed it would. Whether Tau scaling ends up reshaping the global chip industry or becomes one ambitious chapter in a much longer competition between two technological superpowers, one thing is already true. The idea that America's export controls could simply freeze China's chip progress in place has run into a real, peer-reviewed counterargument built not overnight, but across 6 patient years and 381 chips nobody was watching. Tell me in the comments which detail surprised you more, that Huawei had been quietly mass-producing chips on this method since before the sanctions fully hit, or that the world's leading chipmakers still hold the process node lead even after all of this. Either way, the race everyone thought they understood just changed shape.